Section 4.5, page 396, if you wish to follow. The author of the book has got a different way of graphing this than I do. You're welcome to read his, probably give you some really great information. I'm not saying his is wrong or I'm right. I'm just saying I've got a different way of showing you. So if we wish to graph just a plain old y equals tangent curve, like what?
Did you start the video?
I did. Okay. We start the way we did with sine, cosine, sine and cosine by putting it on a grid. But this time it's not going to be short here and really long here. Both are going to play a role. As a matter of fact, I'm going to move that over a little bit so that it doesn't interfere with what I got there. Anyway, tangent x. Now, do you remember we said the other day that part of the way around the unit circle, if we do that, that there are places where it's undefined, the tangent? Where is it undefined?
Where it's standing up, right? Straight up.
Yeah, because tangent is slope, and the slope of this is undefined. That's how you can remember it. So it is undefined at pi halves and 3 pi halves, which for your benefit and seeing what was going on here, that 3 pi halves is also, and I'm just going to put, is also negative pi halves, isn't it? And isn't this also negative 3 pi halves if you go the other direction? Okay. So we've got places where tangent is undefined, and when we have places where things are undefined and we're graphing it as a function, what do those things end up being where it's undefined? Asymptotes. So if I'm going to wrap this thing around the origin, 0, 0 here, then I'm going to, instead of calling this 3 pi halves, I'll put that in a minute, but instead of calling this angle 3 pi halves, I'm going to call it negative pi halves, and I'm going to call this angle pi halves. That way I can get a distance over here and a distance here and have the origin in the middle. That's what I'm doing. I'm trying to straddle the origin. Are you with me? So I'm going to put a negative pi halves here. That's what it would be if this is your axis with the angles on it. And another one, the same distance over here at pi halves. And because we know that tangent is undefined at these two locations, I'm going to put asymptotes in my graph. What I'm going to be graphing here for you is what's called the first branch of the tangent of x, and there are millions of them. What we're going to do is 1, and look at the repetition that goes along. Okay, so I've got 2 asymptotes there because tangent is undefined there, and these are going to be the actual values of the actual values I get by tangenting. So for example, let's say what's right here at this angle right here, which is 0. What is the tangent there? Do you remember? If I put a 1, 0 here, what's the tangent? 0. So at 0 degrees, which is right here, because this is the axis with angles on it, at 0 degrees, the tangent is 0. Okay? You with me? If I go out to 45, like I did with the other ones, if I left out right there, what's the tangent of that angle here, pi fourths? 1, because it's a 45, 45, 90. Tangent's made up of the legs. So halfway out here would be pi fourths, and the value of tangent there is 1. I'm going to go right there. Okay. If I come back and head this direction and try to figure out what's going on, what would be the tangent of this angle, negative pi fourths? This is positive. This is negative. What's the tangent of negative pi fourths? Negative 1. Right here, halfway in between, right here, pi fourths, I get a negative 1. Now, looks kind of like there's going to be a line there. However, we got these asymptotes which we can't cross. Vertical ones are never crossable. So I want you to think with me for just a minute about a triangle that happens that's made of an angle that before pi fourths, like this one. Doesn't have to be anything special, just something less than pi fourths. Can you see that the tangent is going to be small over bigger, which is less than 1? And can you see if I draw one that's bigger than pi fourths like this and drop it down, that the tangent's going to be bigger over smaller? And the steeper I get, the bigger this big over small is going to be as I'm approaching pi halves, that this big one over this, This one's continuing to get taller towards 1. This is continuing to get smaller and smaller and smaller. And the closer I get to pi halves, the smaller this gets. And so the fraction associated with it, the big over this approaching 1 over something smaller and smaller and smaller, is going to get bigger and bigger and bigger. Does that make any sense to you? Yeah? It does? Okay. So as I get past pi fourths and headed towards pi halves, the values of the angles right in here are going to get bigger and bigger and bigger, approaching that asymptote. And the angles before that are going to be something less than 1. Closer to 0, the smaller the angle. And so the thing looks just like you might expect. Comes up, goes through that, and approaches that asymptote. I didn't do that very well. More like that. And then down here, very same thing's going to happen. This will be small but negative until it gets to pi fourths where it's 1. And that's your first branch. It's not very exciting. First branch of tangent. Where will the next one occur? Well, we come out here to where will be the next asymptote? If I'm going forward in the positive way around the circle, the next one will occur to where? 3 pi halves. Here is pi, where tangent is 0. There's another asymptote. It's going to go, notice I went halfway out towards the asymptote, halfway and up 1. So I'm going to do the same thing again. I don't care what halfway is. I don't even care if you can mark that right there. We're going to go halfway out and up 1. And we're going to go halfway back and down 1. That gives you, it looks like a line, but it isn't. It gives you something to shoot for to put the correct bend in it. And if we were to come back here, the next one back here would be negative 3 pi halves. And the exact same thing is going to happen. It's going to be 0 there. It's going to be 1 halfway out. And it's going to be negative 1 halfway out. Then you put a curve in there approaching the asymptotes. Each one of these is a full period of tangent. And here's the main thing that I want you to not miss, because you get it all screwed up if you don't pay attention right now. How far is it from here to here? How far is it in angles, radian angles? How far is it from negative pi halves to pi halves? Pi. Here's half a pi here. Here's half a pi here. So one period of tangent is not 2 pi like sine and cosine. It is just pi. Because think about this. In the unit circle, from here to here, from here to here, you get all of the possibilities for tangent. You'll get them again from here to here. That's only halfway around the circle, and then it starts again. Positive, negative, positive, negative. You get your positive negatives there, you get another set of positive negatives there with tangent. So the period length is only pi, not 2 pi. Before it begins again, it only has to go pi units along the x-axis before it starts over. So the period is pi on the regular old tangent curve. Period is pi. So if I give you a situation like this, if I ask you to graph this, y equals 1/2 tangent of 4x, and I ask you what the amplitude is, you don't say, you say there is no amplitude, but the horizontal shrink, vertical shrink of 1/2. That's what you get. It is not an amplitude when you're talking about tangent, because tangents don't have peaks and valleys. So there's no amplitude, but that thing in the front of it now takes on the same thing it always has for functions, and that is a horizontal shrink in this case of 1/2. Vertical shrink is of 1/2. Right? Vertical shrink of 1/2. 4 in the back serves the same thing that B always has with sine and cosine that you've practiced, but it's not 4. It's not 2 pi. It's not 2 pi over 4. It's pi over 4, because the regular period length is pi, not 2 pi. And so when we go to write these things down, we would say that this is a vertical shrink of 1/2, and the period of this thing is pi over 4. Pi fourths. You got it? And that's a horizontal shrink of this thing of 1/4. It's like taking this thing and cutting it down to 1/4. It's going to be pretty tiny in there. This is how you would go about graphing that particular function. You okay if I erase this? Yeah, this is the regular tangent curve. It's in your book. You can also refer to it on the video here. I'm going to erase it so I can stay on film this with this next graph. Notice what I wrote down here. I wrote a vertical shrink of a half as a reminder. And I also wrote what the period length is as a reminder when I go to graph it, just like I did with sine and cosine. I'm going to write down why that's different from the normal one. So now, as I go to graph this thing, it's going to kind of look like the other one, but it's the way you label the axes that's most important. If the period of this thing is pi fourths, then how far to the right will I go for my first asymptote? Pi eighths. Good. Pi eighths and back pi eighths so that the pi fourth is the full length of that. They're splitting it down the middle. Y'all following? Put an asymptote there. And here's how the vertical shrink's going to happen. I don't care where these things are. If you go halfway out to the asymptote from this origin, if you go halfway out, you go up this far because somebody vertically squashed it. So I'm not going up as high. If I put a 1 here, then you're going to go halfway out and halfway up in this case. It's always halfway out to the first asymptote, and then it's up however far that number is in front of tangent. So this is a half, this is 1, and that's what the half does to you. You're going to go halfway out to the asymptote right there and go up that stretch, or shrink in this case. So you go halfway out, here's -1, if I can get it about right, and you're going to go halfway down right there.
You always go halfway out on the x-axis.
You always go halfway from the center between the two asymptotes. You go halfway to get your first point, then you go halfway to the asymptote from that center point and go up the vertical stretch or shrink.
Okay.
Okay? And then you connect those. That would be the first branch. I assume you could do the next branch. What would be the next marker over here for an asymptote?
Pi fourths.
It's got to go from here to here. It's got to be pi fourths. And we're already out pi eighths. So what will this be? This is pi eighths. That would be 2 pi eighths. Add them together, you get
3 pi eighths.
3 pi eighths. That would be the next asymptote. And we do the exact same thing. We go to the center here. We go halfway out and halfway up to 1. Go back and down. And connect that one. That would give you 2 branches. You could do the same thing back here. It would be negative 3 pi eighths back here for your next one, right? So if they ask you to do 1 or 2 periods or whatever, you can do any ones you want, but I would recommend that one of them be the one that goes through the origin.
Can we do another one of these?
So we have to put on what the book says this time. That was just 1 period.
No, you don't have to do what the book says, but you have to do 2 periods. I want to make sure that you can get another period out properly. You have to do 2, and I don't care which direction you go. I would have one of them go through the origin, unless it's been phase shifted. That's a fun thing. Okay? You okay with tangent or?
Can we do those real quick?
No, we're gonna do cotangent, sorry.
Okay.
Cotangent is like unto it, but not quite. Do you recognize cotangent as being tangent's reciprocal? Now think about this. If tangent and cotangent are reciprocals, and they are, then every place tangent had an asymptote, cotangent will have a 0. And every place tangent had a 0, cotangent will have an asymptote. Does that make good sense?
It's just been shifted.
And because they are only reciprocals of each other, they will have the same period length. So the period is pi for tangent and cotangent. I'm going to leave the period as pi up there. I'm going to erase that so we can get to the regular old cotangent curve. So this is what we're going to graph. Try to remember what tangent looked like. Kind of some of the details. So at the origin, if you understand what I just said about reciprocals, what will we have at the origin? An asymptote, because tangent had a 0 there, right? So we're going to have an asymptote here. And if the period length is pi, which it is, just like tangent, because the reciprocals, you get 2 full periods all the way around the circle of cotangent as well, where will the next asymptote be to the right? At pi, because the period length is pi, and besides that, if you'll remember, I don't know if I probably didn't actually mark it, but on tangent, there was a 0 at pi. Isn't the tangent of pi 0?
Yeah.
Then the cotangent is undefined. So here's pi. I will have another asymptote there. So what we see here, I don't know if you can tell yet, but what we see here is that cotangent is a pi halves shift of tangent. Let's just move it over pi halves. Where we had zeros, we now have asymptotes. Where we had asymptotes, remember the first asymptote between these two is a pi halves? Now we have a 0. This is that pi halves. And for cotangent, we have a 0 there because tangent had an asymptote there. Here's the weird thing. I'm going to draw just a brief view of tangent so that you can compare the two. Asymptote there and there. And this went up. This went down like this, right? Something like that. All right. Remember, this is pi halves now. We're talking about reciprocals again. If I go halfway out and halfway up on just a regular old tangent curve, then this is 1. This is pi fourths. This is 1 right here. What's the reciprocal of 1?
1.
Then at pi fourths is right there, right? Pi fourths, the cotangent will have a value of 1, just like tangent did, because the reciprocal of 1 is 1. Now, I'm going to have to draw another one out here so you can see what's going to go on for the next part. This would be, that was a pi halves, this is 3 pi halves. So this is pi. We got a 0 here for tangent. We had an asymptote for cotangent, which is right. But what happens right here? If I was to draw another branch of this, wouldn't it come down and this one go up? Then right here, which is between pi halves and pi, here's pi halves and pi, I have a negative 1. What's the reciprocal of negative 1? Negative 1. And so down here, it's going to be down at negative 1. And so what happens is, it has the same behavior, but it feels like someone's reflected it. Because before we started low and ended high, cotangent starts high and ends low. Because of this reciprocal nature and the pi half shift. So this is one branch of the cotangent curve. And it starts high and comes down, just like tangent started low and went up. It's the same shape. It's the same shape, but it feels like somebody reflected it. They didn't. It's just the way the positives and the negatives turned out to plot. Once we shoved it over pi half, it ends up having positives on the left and negatives on the right, which is the opposite of what tangent is. You still go out halfway and down, whatever the stretch or shrink is. Y'all following? Okay. So let's see if we can graph with these details, see if we can graph the transformation of that. So I want to graph y equals, I'll put it over here, y equals negative 2 cotangent of 1/3 x. So what, right down here, what am I going to write to accomplish, to remind myself of this? Okay. Vertical stretch of 2. What else? Reflected over the x. And the period is what? Period is pi over b. Is that okay? Okay. So we start to draw, and we remember that cotangent is different from tangent in that where this had a 0, this one has an asymptote. So we start with an asymptote here because there's no phase shift. Asymptote there, and where's the one to the right going to be? At 3 pi. Y'all see it?
Yeah.
It's going to have to be at 3 pi. Yes, this is cotangent. So I'm going to come out here some arbitrary length, but I'm going to label it 3 pi based on what I know for the period length, which means this is what? 3 pi halves. Good. Okay, and there's going to be an asymptote here if I'm going to work on just this branch for just a minute. Asymptote there. Now, is this going to be a stretch or a shrink? Stretch. Then I suggest when you label this one right here, don't get too carried away. If you put the 1 up here, you're going to have to go clear up here for the 2, and that's going to be kind of boring. So be reasonable, realizing you're going to have to go up to 2 to plot a point. Put your 1 here, and your 2 about there. So that means I'm going to have to go halfway out and 2 up, right? Is that how cotangent behaves? Yeah, it does. When you reflect it over the x. Gotcha. Cotangent normally behaves like this, but we're reflecting over the x. If you tip that over, now this branch which came down this way is now going up that way. So it is behaving like tangent because of that thingy right there. So be careful. This one's going to go halfway back and down too. So I'm going to need to number these about the same. You didn't understand that? Did somebody say that? They don't get it?
Yeah.
You always go halfway out to the asymptote from the center point. And up the stretcher shrinker, right? But this one is going to behave like tangent, which starts low and ends high because of this reflection. If this weren't here, if I take that off right there, then we would start high and low, and you would have gone back and up instead of forward and up. You understand what's happening? Because of the reflection over the x? So then you connect these, approaching the asymptote, and as long as your axes are all labeled properly and you get your point, got a couple of dots, I expect to see at least 3 dots, you're all set. Make sure you just number these things properly. And you could come back here and come back 3 halves, or 3 pi, and do the very same thing. And it's not that hard. Okay? Think you can swing that? All right. Pretty darn sure they don't have a phase shift for you.
Yes. Yay. Let's go.
If they do, and I am wrong, I will go through it with you tomorrow slowly so you can understand it. But if they don't have one, and I just don't do. It's not me that I don't do. It's just that tangent and cotangent don't show up that often, and they certainly don't phase shift very often. So I'm gonna dodge that bullet. And if I have an assignment and you have to face that somewhere where you actually have to do a graph, we'll talk about it tomorrow. Okay, now I want to talk to you about the other 2. What are the other 2? What are the other 2 that we still have left? Secant and cosecant. Once I've shown you secant, you're going to see how cosecant falls in line, and I'll do one for you if you want, but it probably won't be necessary. Have y equals secant x. If I do that without any embellishments at all, what goes with this as a reciprocal?
Cosine.
Cosine. So watch how this, knowing this goes with cosine, watch how this is going to graph out because they are reciprocals. This is what I'm going to do. And this is going to seem really bizarre at first, but just go with me on it. You'll see the value of it. What I'm going to do is graph the cosine of x. You're going, well, that seems dumb. No, it won't seem dumb at all. You'll see it. You got a 2 pi over here, if you remember practicing that. I hope you all practiced it. You got a pi here, pi halves, pi fourths. Goes on up, that's what, it's pi halves, this is 3 pi fourths, and so forth. I'm going to go ahead and let those stand. And then I'm going to put a 1 right here. I'm going to put these low on purpose. You'll see why in just a minute. 1 and -1. And so I would start here with cosine, go 3/4 of the way up here, down to the 0, 3/4 of the way down here. That looks funny. Pi is going to go all the way down here, then 3/4, then up 3/4 of the way and all the way. So that this is what the cosine curve looks like. You're thinking, why would you graph that? And the answer is, well, you'll see in just a minute. Hang on. But when you draw this in an attempt to actually graph secant, you should dot it because that's not what you're really graphing. But you will see in just a minute, it's a huge aid in getting the graph of secant done. So you should dot this. And it's fine to include it, but you should dot it because it's not really what we're graphing. So we dot graphical aids, but we don't actually make them solid in that thing. Okay, so here's the deal. If secant is cosine's reciprocal, then every place cosine has a 0, secant will have an asymptote. Again, dotted. This is just an aid in graphing. So over here, there will be another asymptote. Wherever cosine has a 0, secant will have an asymptote. Now, what is the reciprocal of, I'm going to work on this one right here in the middle. What is this value right here? The y value? -1. -1. What's the reciprocal of -1? then secant also has a value of -1 right here. Where does it have a value of 1? I'm graphing secant with the blue here. No, right here. Because the reciprocal of 1 is also 1. These are points on secant. Now, what is the reciprocal of, remember this was root 2 over 2? What's the reciprocal of root 2 over 2? Because that's what secant's going to be at this point.
2 over 2.
No, which is
2. Square root of 2.
root 2, which is about how much decimally? 1.41, about. Okay? So this was 1. 2 would be up here. 1.41 would be about right here. Now, think with me and just doing generalities here. Do you see that this number is smaller than root 2 over 2? Doesn't that make sense that its reciprocal would be bigger than root 2? The reciprocal of something small is big. So this one's going to be up here. And it's going to be asymptotic because we got an asymptote there. It's going to look like this. And this one down here, for the same reason, since that's very small, it's going to be a rather large negative reciprocal. It's going to come down like this. And this one's going to go up like this. And it's going to continue up like this because the secant or the cosine continues down like this. See how they bend away from each other reciprocally?
That makes sense.
That make any sense to you?
Yeah.
So here's the deal, folks. You might want to wait for just a second. Here's the crux of the whole thing for secant and cosecant. If you have y equals, for example, 3 secant of 2 pi, all right, 2 pi x, I'll do that. Then that means you should graph this. Graph that. Put the asymptotes where the zeros are. Put these beginning points at the peaks of these and just go up. I really don't care if you get correct points in there. Just make them go up. These are called scallops. And they alternate. Scallops. That's all you got to do is get them started in the right place and approach the asymptotes. That's all I care about.
Is it the same with cosecant?
Exactly. If it's cosecant, draw the sign of the same transformations.
And then
Exactly the same thing. Scallops go up from the peaks.
Okay.
And asymptotes occur at the zeros. That's all you got to do.
Is it period 2 pi? Yeah, 2 pi.
Okay? So I hope those of you viewing that understand that. If not, bring your questions to class. That's it. Bye.